Hello everyone, my name is Kosi Aroh from the University of Maryland College Park, and this summer I worked in the SROP program in the Glotzer lab under the mentorship of Joshua Anderson, and I worked on programming crystals using DNA patches. This is a rough outline of what I am going to talk about today, basically the motivation, some background, some details of the research, and some of the problems I faced. So why study DNA-assisted self-assembly? Well, for one thing, it promises the ability to easily program desired materials for a variety of applications. And it doesn't depend on the chemical properties of DNA, of the nanoparticles that you use. I'll explain that a little bit later. So self-assembly. So basically, you initialize your system. Here's a Wikipedia definition. But basically, you initialize your system and then you allow time for the interactions to occur, and then you wait till equilibrium is reached. You basically let the system, let the interactions occur themselves, and everything else you just watch. So why DNA? Well, for one thing, it bonds by complementary base pairs, and the bonding is hydrogen bonds. Hydrogen bonds aren't permanent, and they change with temperature. Basically, this allows for selectivity. When we attach DNA to nanoparticles, it allows certain bonds to be made. So it allows you to be able to direct the way you want, or direct what type of structure you want to form. So then what parameters matter for these type of simulations? Well, kinetic energy, how quickly the bonds break, the equilibrium radius, cutoff distance, how long the simulations run, and how you basically configure the base pairs of the DNA. So the type of crystals I studied were simple cubic was one. It has a coordination number of 6. Basically, it has 6 closest neighbors. And I also studied face-centered cubic, which has a coordination number of 12. And the difference between these two is basically, well, for this, I need 12 patches of DNA, and I have to configure them just that the DNA and its complement basically are 180 degrees apart. And so when like a particle with a DNA bond here, another particle with its complement down here should be able to bond and attach such that they form a crystal lattice that is shown here. So some results. For one thing, I varied the bond dissociativity to simulate annealing process, which also depends on temperature. But in our simulations, we basically split the temperature effects into 2 parameters. One was D and one was T. And basically D, how quickly the bonds break, changes with temperature, and T, which is just the kinetic energy of the particles, also change with temperature. But some results that are shown here is, for one thing, when I didn't anneal it, on these graphs are basically the number of particles versus how many bonds they have. And this is for simple cubic, so they all need to have 6 in a crystal. And we see with no annealing, the average is about like 4. But when I do anneal, most of the particles are around 6. So obviously it shows that annealing allows time for these bonds to form, or it's more likely that bonds form. And here is a graph of when I vary temperature. And basically this first graph is, you might not be able to see it, but this is the lowest temperature. This graph is the highest temperature. And this graph is the medium temperature, which is, for this is T equals 1. This is T equals 3, and this is 2. And basically what this is showing me is that at T equals 1, I'm able to get more bonds to form. Basically, it means that the particles, when the particles move around too much, it basically they get away from each other. They're more likely to get away from each other. When they're moving around less, I guess they're able to, once a bond break, they're more likely to form that bond again. And so they're all right there. Some problems I faced was equilibrium. So basically how to determine whether equilibrium has been reached. This is a common problem for self-assembly. And the main problem I had was bonding. So these particles tend to get into a configuration where they have two bonds shared between two partners. And that basically destroys my crystal structure, and no structure can form unless I'm able to get rid of that problem. I'm currently working on ways to find out what to do about that. I have some ideas, but I'm still working on it. And through this, I learned a lot. One thing about self-assembly, simulations in general that I haven't done before. And for that, I'd like to thank the Glotzer Lab for this opportunity, Dr. Joshua Anderson, Sharon Glotzer, the SROP program, and I really had fun this summer. And thank you for listening.